Okay, so, and then the last thing is that if you are stuck on something in this unit and I don't know the answer, I will find Hughes and get him to answer it for us because he loves this stuff. He lives for this. Um, I actually had a student the other day from another school email me with a question, and it was from this unit. And I thought I knew how to do it, and I did it. And then I went to Mr. Hughes to make sure I did it right before I responded. And he's like, "Oh yeah, 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 you're fine." But that's how I'm not confident in this. Okay. Can I do the questions on the diploma? Yes. Do I want to do them? No. Okay, so today is a language day. Okay, just a whole bunch of words. Um, you will see me hand out, there's a fair bit of handouts in this unit that supplement the workbook, just because the workbook, they explain it in rather convoluted ways. So I'm going to explain it in a simplified way and then just show you how to explain it in the fancy way. Okay? So probability is the measure of how likely an event is. The probability of an event can range from 0, or we can write it as 0%, or we can use the word impossible, to 1. So we can say it's 100% certain. Okay. So in other words, what I'm trying to tell you here is that when we do probability, you can write the answer as a decimal, a number from 0 to 1. So like 0.5, 0.82. Or you could write it as a fraction, 3/4, 2/5. Or you could express it as a percent, 27%. Probabilities that equal 0 are called impossible events, meaning there is no chance for that to occur. Okay? Probabilities that equal 100% are a certainty. Now, I know you've heard the words impossibility and certainty in your language before. Okay? So it can be written as decimals, percents, and fractions. On the diploma, anyone goes. And I'm assuming you know how to convert from decimals, percents, and fractions. I'm assuming you know how to do that from other grades. So remember what I said before. The diploma is written in perfect math language, where while that may sound scary, it's also written in a way so that everybody can understand, so that there's no gray area. Okay? So if you have 2 dice and you roll them, rolling a 14 is an impossible event because the biggest you could get is a 6 and a 6. So the biggest you could get is a 12. So if I said, what's the probability of getting a 14 when you roll 2 dice, you would say 0. It's impossible. The sun will rise. Certain. Now, I question that because that's tomorrow. We don't know what's going to happen tomorrow. We only know what to say. So I would say the sun has risen. That's a certainty. It has risen. It's up there. Okay. Even chance, probability of getting a head on a coin toss. That's a 50-50 shot. Okay. So even chance means like 50%, 100%, 0%. Okay. Okay. So if you go to page, oh, I didn't put the page number on here. Pardon me? Page 123. Now, do we even want to use that? Yes, we do. Page 120. Oh, no. Yes, page 123. So I've got all of them written out here. I used a different font than what's in your booklet, but they're all exactly the same. So we'll just go through this fairly quickly. It's pretty self-explanatory. So a trial is actually doing an experiment. So a trial would be tossing a coin to see what you get out. A trial would be rolling a dice to see what you get out. Trials and experiments are pretty much the same thing. Okay, so if you hear the word trial, you hear the word experiment, they pretty much mean the same thing. Outcome, it's exactly what it is. It's what happens when you do the experiment. Okay, so for example, if I roll a dice 5 times, the outcome could be a 2, a 2, a 5, a 1, a 3. That's the outcome list. When I list out the outcomes, you write them as a set theory. So if I were to roll So if I were to toss a coin, the sample space would be heads or tails. So you put fancy brackets HT. If I were to roll 2 dice, all the outcomes would be getting a 1 and a 1, a 1 and a 2, a 3 and a 4, a 4 and a 5, all the way up to a 6 and a 6. Okay? What if you were to toss a coin and roll a dice? Well, you could have a head and a 1, or a head and a 2, a head and a 3, a head and a 4, a head and a 5, or a head and a 6, or a tail and a 1, a tail and a 2, a tail and a 3, all the way up to a tail and a 6. So listing out all the possible outcomes, that's what we call your sample space. It's everything that possibly could happen. Okay? An event is picking something that happens in the sample space. So for example, rolling a 1 and a 4. That is one of the outcomes in that sample space. Tossing a tail and rolling a 2, that's one of the outcomes in that sample space. That's called an event. Okay? An impossible event, that's the 0%. So is there any way to roll a 7 and a 7? No. Is there any way to toss a tail and roll a 12? No. Okay? So the probability, so the way we write it is we do P and then we put the event here. Equals and then the answer here. So P brackets event means the probability of the event. So if it's an impossible event, it equals 0 or 0%. If it's a certain event, you write the answer as 1 or 100%. So P brackets something, the P stands for the word probability. What's inside the brackets is the event that you're finding the probability of. Okay. So technically, there's 2 types of probability. There's experimental probability and there's theoretical probability. Here's what I mean. You have a coin. Okay, you toss the coin. What are the 2 events that could happen? Head or tail, right? So let's say you toss the coin 5 times. Okay? Let's make it easier than that. Let's say you toss the coin twice. So you could either have a head and a head, a head and a tail, or 2 tails, right? So each of those, there's 3 outcomes. So technically, you've got a 1 in 3 shot of tossing a head, right? A head and a head. Okay? That's what we call the experimental probability. Theoretical probability. So theoretical probability is what happened, is what should happen. Experimental probability is what actually happens when you do the experiment. So theoretical probability. So if an experiment has a set of equally likely outcomes, and that's the catch here, every outcome has to be equally likely to occur. So in other words, you can't have a loaded dice. Do you know what a loaded dice is? A loaded dice is a dice that has been weighted on one side so that when you roll it, it always comes up a 2, or it has a better likelihood of coming up a 2, or whatever you've done to jimmy that dice. Okay? Or it's using a fake coin where both sides say heads. Okay? Those are not equally likely outcomes. We're going to pretend that everything that we do in this course has an equal likely chance of happening. There's no unfairness happening here. There's no loaded dice. So the chances of something happening, the way we write it is, so the probability of event A occurring is, and we write it as, the number of favorable outcomes over the total number of outcomes. So the way I kind of word it, I think of it like this. It's everything that you want to have happen over everything that could happen. That's how you get the fraction. Okay. Now, this is why you always end up with a number between 0 and 1. Because what you want to have happen can't exceed what could happen. It's like in our last unit, if I needed to select 3 of you from a group of 8, it's 8 choose 3, not 3 choose 8. I can't select 8 people from 3. I can only select 3 people from 8. So what you want to have happen versus everything that could happen. Okay? So we call that theoretical probability, not experimental probability. Experimental probability is completely different. Like, do you understand that when you toss a coin, there's a 1 in 2 shot of getting ahead? But if you toss that coin 5 times, could you get out tails every single time? So then the chance of getting ahead would be 0 because you got tails every time. That's what we call experimental probability. What we're going to work with is just theoretical probabilities, what should happen, not what actually does happen when you do the experiment. Because when we get into experimental probability, it becomes just a big old mucky mess. So we're only going to work in theory. Okay, what should happen. Okay. So for each of the following, so you've got this example in your workbook, I think. Okay, I think it's example number 1, is it? Okay, so we're going to give the sample space, the favorable outcomes, if the outcomes are equally likely, and the probability of the event. So a fair standard dice is rolled. By the way, die is the singular version. Technically, when we say dice, that's plural. So we say 1 die, 2 dice. We don't say 1 dice, 2 dices. Okay? So if you see the word die, that's just the singular version of dice. Okay? What is the probability of rolling a 1? So the sample space would be a 1, a 2, a 3, a 4, a 5, or a 6. That's everything that could happen, right? You land on a 1, a 2, a 3, a 4, 5, or 6. The favorable outcome is rolling a 1. Sorry, I should have fancy brackets there. So the favorable outcome is what you want to have happen. Are the outcomes equally likely? Yes. Every number has a fair shot at landing on. So then what's the probability of the event? So the probability of landing on a 1, so that's how we would write it, the probability of getting a 1 is number of favorable outcomes. So there's one thing that we want out of a total of 6. Now, could you have figured that out without me talking? Do most of you instinctually know that you got a 1 in 6 shot of landing on a 1 when you roll a dice? You don't need Math 30-2 to tell you that. So I need you to please keep your common sense button turned on. Because you already know pretty much how to do this unit. My job is to say, okay, well, when we start getting into bigger probabilities and a little bit more complicated questions, my job is to break it down for you, but you should naturally understand what the answer already is. Okay? Okay, well, let me just move that down so it's a little more easy to see. So same thing on this one. A circular spinner is divided into 4 equal sectors, labeled clubs, diamonds, hearts, and spades. Do you have this question? You do? Okay, so on the diploma, they will actually give you the picture of the spinner. So they'll describe it in words, and then they'll have the picture of the heart, the diamond, the club, and I don't know how to draw a spade. Something like that. I don't know, whatever. Okay. So they will actually, because again, that's for the kids who struggle with English, right? They're going to draw the picture as well as describe it in words. Okay. When it is spun, what is the probability that it lands on hearts? So again, it's just a matter of understanding that are all the sections the same size? So that is important because we need it to be equally likely. If the heart section was 3 times bigger than all the other sections, this would be beyond math 30. Okay, so I don't need to do all this. What's the probability of it landing on a heart? How many favorable outcomes do we have? How many total outcomes do we have? Done. So you got a 1 in 4 shot of it landing on a heart. Now, if you wanted to, you could make this into 0.25, or you could make it into 25%. They are all equally correct. So multiple choice or numeric response, typically numeric response wanted as either a decimal or as a percent, whereas multiple choice will usually give it as a fraction. Okay, I'm not going to waste time really showing you how to convert. I'm going to assume you know how to do that by this point in grade 12. But I don't need to know all that stuff in order to be able to do that question, right? It's common sense. Look at that, we're halfway through the lesson already. Almost there. Okay, so next page in your notes, you should have some more words now. And again, I'm just here to break it down, but we've already done this. We did this in set theory, and that's complementary events, or the complement of an event. Okay, the complement of an event. Complement is another word for not. Okay, so this is the not. So the event lands on hearts had a probability of 1 in 4. Does not land on hearts would be 3 in 4. Okay, so the way we show that is we would say probability of a heart is 1 in 4. The way we show complement is we show H with a little dash. That means not. Now, this is exactly the same as set theory. Let me see if I can find a little space to put this in here. Let me just go down here. Do you remember in set theory, this was our universal set. This was set A. This was not A. Remember that? And both of these, when you added them up, you had to get out the universal. Okay, same thing. The probability of an event plus the probability of not the event. Okay, so think of this in terms of probability. So this is 1 in 4. This is 3 in 4. So this is chance of getting a heart, chance of not getting a heart. What is 1/4 plus 3/4? 1. It will always equal 1. Why? If this is the event of something happening, and this is the probability of it not happening, then when you add them up, you get certainty. Let's take the dice. What's the probability of it landing on a 5? 1 in 6. What's the probability of it not landing on a 5? 5 in 6. What's 1 in 6 plus 5 in 6? 1. If I said, what's the chances of it landing on a 5 or not landing on a 5? You're going to look at me and go, well, landing on a 5, not on a 5, that means it could land on anything. So 100%. Certainty. So when we did set theory, those two things added up to however many elements there was in the universal set, and that number changed question to question. But in probability, they will add up to 1 every single time. Okay. Okay, so sometimes it's written with this, so probability of A prime. Every once in a while, you might see it with a bar. A bar in math means not. So that little dash could mean not, or the line above it could mean not. I know the workbook does both. I'm pretty sure Please don't quote me and I'm not going to bet my firstborn on it, but I'm pretty sure the diploma prefers this one. Okay. So it says here for part B, determine the probability of the complement of rolling a 1. So that's like saying the probability of not rolling a 1. What would that be? So not rolling a 1, 5 out of 6. Now, if you don't like doing it that way, you could find the probability of rolling a 1 is 1 in 6. So the probability of not rolling a 1, you would go 1 minus 1/6 to get out 5/6, because 1 is the 100%. And it's always going to be a 1, like a big 1. So you're going to see me in this unit constantly tie back to set theory, because that's all probability is. Does that make sense? It's just the opposite. Okay. So the last word that we're going to talk about is compound events. Okay. So these are ones that can be a little trickier. So, and this is where we're going to start when we get into some pretty detailed compound events happening. That's where you need me to step in and help you kind of dissect the situation. But a compound event is events like 2 or more events happening at the same time, okay, or one after another. So it says events formed from repeated trials or from a combination of simple events are called compound events. And often a table, chart, or tree diagram is useful in determining the sample space. So it says consider the following. 2 coins are tossed and the number of heads is counted. What is the probability of obtaining 2 heads? So the sample space is 2 heads, or 1 head and 1 tail, or 2 tails. Do you agree with that? Yeah. The favorable outcome, so what we want to have happen is 2 heads. So it says since there are 3 events in the sample space, and only one of these is favorable, Tyler concludes that the probability of obtaining 2 heads is 1/3. Tyler is wrong. Tyler's an idiot. Just kidding. How come? Okay, when there's 2 coins, again, what the diploma will do is they will typically show you a picture of 2 coins, and you will see that they don't look alike. They will be a quarter and a dime. Why does that matter? So coin number 1, coin number 2. So you could toss and get a head and a head, or you could get a tail and a tail, or you could get a head on coin 1 and a tail on coin 2, or a tail on coin 1 and a head on coin 2. So the probability of 2 heads is 1 in 4, not 1 in 3. Snaky. Now, if your little brains are going, would they ever give us 2 identical coins? No, they will not. You're always going to assume that the outcomes are, like for example, if we were rolling 2 dice, they would say a blue dice and a red dice. So you can clearly tell the outcomes on each dice. Okay? So that in other words, if I say, what's the odds of getting 2 5s? You could get a 5 on the red and a 5 on the blue, or 5 on the blue and a 5 on the red. Those are considered 2 possible favorable outcomes. Okay? So that's a little sneaky, but we'll keep circling back to it. Okay? So that hopefully you'll just kind of sink in as the course progresses. Okay. So they just wanted you to do a tree diagram. We don't need to do that. So we already have our list, right? We've got, we've got head and head. We've got head or tail and tail. We've got head on one, tail on the other, tail on one, head on the other. So what's the probability of getting 2 heads? 1 out of 4. What's the probability of getting 2 tails? 1 out of 4. What's the probability of getting 1 head and 1 tail? It doesn't specify which coin has to have which. So there's 2 options here that have 1 head, 1 tail. And then if you're going to do it as a fraction, we expect you to reduce the fraction down. That's why a lot of kids just do percent or decimal, because it's just easier. Now, did I cover all of my outcomes? 2 heads, 2 tails, 1 of each. Did I cover all my outcomes? So what should all the probabilities add up to? 1, right? Because it has to be, you have to add up to everything in order to get out that 100% certainty. Now, in questions, are they going to ask you to list out every single event? No. They're just going to say, what's the probability of getting 2 tails? Okay. Okay. So, consider an experiment of spinning an equally spaced triangular spinner, and they've got it numbered 1, 2, and 3. We've got blue, red, and yellow here, but I'm just going to number them 1, 2, 3. And tossing 2 coins. So you don't have to know how to draw a tree diagram. They are handy, but you don't have to know it for sure, but I'll show you what it looks like. So if you did the spinner first, and again, it doesn't matter what order you do it in, you could get a 1, a 2, or a 3 on the spinner. On coin number 1, you could get a head or a tail. So you could get a 1 with a head or a 1 with a tail. Same thing for this. Same thing for this. And then for coin number 2, again, you could get a head or a tail. So you could get a 1 on the spinner, a head on the first coin, a head on the second coin. So you could get a 1 with a head and a head. Or you could get a 1 with a head and a tail. Or you could get a 1 with a tail and a head. Or a 1 with a tail and a tail. And now we repeat that process for 2 and 3. Do you see why it's called a tree diagram? If my arms here, think of this as a trunk, it's like a tree on its side, right? Here's the trunk, here's the branches going out. So you could spin a 2 and then get a head and a head, a 2 with a head and a tail, whoops, tail, a 2 with a tail then a head, or a 2 with a tail and a tail. Oh, good Lord. A 3 with 2 heads. Right, there's all your outcomes. Now, if you're thinking to yourself right now, good gracious, do I have to do these things on every question? No, you don't. This is where we start so that you can understand what's going on, and then we show you the shortcut. Okay? So, how many elements in the sample space? So we've got 12. Okay, now, if you didn't want to do this, what you would just do, is you would just count your branches. So you would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So honestly, you either want to do this or this. You don't want to do both. I'm just showing you 2 different ways you could. This is what's called a tree diagram. Okay? This is just listing the outcomes. Okay? So, show how you could use fundamental counting principle. Ooh, now wait a minute. You just wrote a test on this. This is the blanks method. You have spinner, coin 1, coin 2. How many different outcomes are available on the spinner? How many different outcomes are available for the first coin? And for the second coin? What's 3 times 2 times 2? 12 possible outcomes. So you're going to see this happen every now and again. We're going to take a concept from the last unit or from set theory, and it's going to be like, ooh, hold on, yeah, that makes total sense. So on the diploma, okay, on the diploma, the first couple of questions are going to be number puzzles. We haven't done any yet. We'll do them in June. They're puzzles, okay? Like Sudoku. It'll give you a half of a Sudoku, and it'll color in one square and say what number should go in this square. So the first like 2 or 3 questions on the diploma are number puzzles. Yes. Yeah. So we'll do a few examples together, just get you used to it. But there's really, you can't study for those, right? You do them or not. So it starts you off soft. And then the next like 4 or 5 questions you're going to get are set theory. So intersection, union, Venn diagrams, that fun stuff. And then the next 8 questions are going to be either the unit you just wrote, so permutations, combinations, or probability. And they're going to jumble them up because there's so much overlap between this unit and that last unit that they can kind of do that. But I'll show you how to decipher between them when we go through, okay? And the reason why is we keep getting all this overlap stuff happening. So it gets a little bit jumbled. Now, these 3 units, so set theory, permutations and combinations, and probability, they make up half of the diploma. So your first 16 questions are those 3 units. And then after that, you move into the algebra part of the course. So you do the exponents and logs, the rationals, and then the last unit that we have to do. And so half of the exam is going to be split equally between those 4 units. The first half of the exam is split equally between the first 3 units. Okay. Are all the outcomes equally likely? Yes, they have to be. Otherwise, we can't do math. So state the probability of obtaining a 3 and 2 heads. So a 3 and 2 heads. So a 3 and 2 heads is right here. So that is 1 out of 12. Okay, now they're going to start bringing in words now from previous grades. A prime number. What are your prime numbers? Okay, is 1 prime? No. Your prime numbers are 2, 3, 5, 7, 11, 13. Okay, which of those numbers are on the spinner? 2 and 3. So you want a 2 or a 3 and exactly 1 tail. So you want a 2 or a 3 and exactly 1 tail. So this is a 2 with exactly 1 tail. Sorry, I should do it in a different color. This is a 2 with exactly 1 tail. This is a 2 with 1 tail. This is a 3 with 1 tail, and this is a 3 with 1 tail. So how many things did I circle? 4 out of 12. Okay. Now, that question would be kind of tricky to do without the sample space drawn, but it is doable. And as you get going through the unit, you'll see tips and tricks along the way. Okay, if you were asked to create a sample space, so on your unit test, which I know feels like forever away, May 15th, I have this filled in, okay? So a sample space is listing all the outcomes for an event, just like here, right? Here we listed out the sample space of a spinner with 2 coins. The 2 dice is a very common sample space, a very common type of question. So if we just take a minute here, is yours already filled in on your page? No. So let's just go in. So these are blue. So these are blue. These are red. So make sure that you write the blue number first and the red number second. So the first number we write will be the blue. The second number we write will be the red. Okay. So I'm just going to hit pause here and just fill this thing in. Good. Okay, so there's your sample. Okay, so it says how many outcomes are in the sample space. So how many squares did you just fill in? 36. Now, if you didn't want to create all that, we can use blanks method. Okay, so blue dice, red dice. How many outcomes are possible on the blue dice? 6. How many outcomes are possible on the red dice? And you're looking for the outcomes that are on the blue dice and the red dice. What's 6 times 6? 36. So if you didn't want to fill in that big, huge chart, you can just use the blanks method to figure out your total number of outcomes. Okay. The sample space is nice because now all you have to do is physically count the items that match your condition. Okay. So it says list the event, the same number appears on each die. I'm not going to do that. The same number on each die would be a 1 and a 1, 2 and a 2, 3 and a 3, 4 and a 4, 5 and a 5, 6 and a 6. Okay? So this booklet really breaks the questions down. But what it's training you to do is to just really think about the question and just not try to you don't want to be a bull in a china shop with this stuff. You want to just slow down and gaze at the merchandise and take your time before you buy anything. Okay? So state the probability. The probability that the same number appears on both dice. So that would be, I highlighted 6 numbers out of 36. So getting a 1 and a 1, a 2 and a 2, 3, 3, 4, 4, 5, 5, 6, 6. So there was 6 outcomes that I highlighted yellow. So 6 out of 36. So if you reduced it down, 1 out of 6. Now just to show you, just so that we're clear, if you go 1 divided by 6 on your calculator, 0.16 repeating would be the decimal. If you times it by 100, 16.7%. Okay? So you would show it as either this or this or that. They all mean the same thing. So in other words, what's the probability of getting doubles? 16%. That's the probability of getting doubles. Okay, so quite often percents make the most sense. Okay. A different number appears on each die. Okay, well, these are opposites, right? You either have the same number or you have different numbers. So this is complement. So if same numbers is 6 out of 36, what would different numbers be? 30 out of 36. It's everything that you didn't color. Because remember, it has to add up to 1. Like 6, this plus this has to equal 36. Okay, and again, you could reduce that down, write it as a decimal, fraction, whatever. You could just minus from 100%. So you get out 83.4. Right, you could just do it that way. So how can the answer from A? This is just complement, right? That's all that's referring to. They're opposites, so this is complement. Okay. Okay, are we done? I think we're done. Okay, so let's go into the workbook and just do a couple questions together, and then we'll call it good. So page 127. Okay, so let's look at number 4. Okay, so number 4. Okay, so it says packet 1 contains an orange candy, a lemon candy, and a strawberry candy. Package 2 contains an orange, a strawberry, and a raspberry. Without looking in the packets, now why is that important? It needs to be random, right? Every outcome needs to be equally likely, okay? A student takes one candy from packet 1 and the other candy from packet 2. So draw a tree diagram as to what to expect. List the event, both candies are the same type. List the event strawberry, state the probabilities. Okay, let's just go straight to part D. Okay, first off, we need to figure out the total number of outcomes. Packet 1, packet 2. They're going to take a candy from packet 1 and a candy from packet 2. How many candies are in packet 1? 3. How many candies are in packet 2? 3. So there are 9 possible outcomes. Now, could you list them all out? Yes. So you could go orange and orange, orange and strawberry, orange and raspberry, lemon and orange, lemon and strawberry, lemon and raspberry. You could go strawberry and orange, strawberry and strawberry, strawberry and raspberry. So if you wanted to list them all out, you could. Okay. But I like doing that so that if I do want to list them out, I know how many I should be expecting. Okay. So part D, both candies are the same. So the probability that the candies are the same. Okay, so that would mean, so count on your fingers. So orange, orange is one option. What's another option? Strawberry, strawberry. Is that any others? So 2 fingers up. So 2 favorable outcomes out of a total of 9. Don't overthink this. Okay, just dial it back, please. A strawberry candy is not chosen. Okay, so probability of not picking a strawberry. Okay, so you could pick, so just list them out. You could pick an orange and an orange and a raspberry, a lemon and an orange, a lemon and a raspberry, and that's it. Right? Because you can't pick the strawberry option. So that's 4 fingers up. Now, if there was like 8 candies in one and 7 in the other, I would take the time to list because it would be way too many things to count. But when it's something small, like I have 10 fingers, the maximum is 9. I can do this on my hands. Okay. But if it was like 36 possible outcomes, I'd be listing. Okay. At least one orange candy is chosen. Okay. At least one orange. So that would mean 1 orange or 2 oranges. So one orange would be an orange and a strawberry, an orange and a raspberry. 2 oranges would be an orange and an orange. So 3 choices out of 9. So 1/3. Part 4, the candies are different flavors. So different flavors. So that would mean an orange with a strawberry, an orange with a raspberry, a lemon with an orange, a lemon with a strawberry, a lemon with a raspberry, a strawberry with an orange, a strawberry with a raspberry. So 7 out of 9. Now, take a look at this. Take a look at that. Those are complements. So could I have just gone, if it was 2 nights for the same, could you therefore just jump to say 7 nights for not the same? Right? So instead of counting, I could have just used the idea that those 2 are complements. So if this was 2, this had to be 7 because 2 plus 7 is 9. Okay, which is what part E is. Part E just wants you to tell its complements. Okay, whoops. Okay, so if you want to do more practice with this, number 3 and number 5 work this are similar to that. Let's look at number 6 together. Okay, number 6. Yep. Yes, you're not looking too good. Okay, so we're just doing examples here. So, yep. And then 7 to 11, they're multiple choice. So if you get stuck on any of them or numeric response, just go and look on the Google Classroom and there's a written explanation there. Okay. Okay, so Rebecca, Elizabeth, and Jenny each toss a coin to see who is going to pay for coffee. Okay, that's fine. If one of the students throws a different outcome from the other two, then the student buys all 3 coffees. If all the students throw the same outcome, then each student pays for their own coffee. I pay for all 3. That we all pay for our own. Yeah, okay. So use a tree diagram to construct the sample space. So however you want to organize this in your brain. So I've got, what were their names again? Rebecca, Elizabeth, and Jenny. Okay. So, tossing a coin, right? So they could all get heads. So what I'm going to do is I'm just going to list them all out. Now, I want to know what my total is before I even go. How many outcomes does Rebecca have possible? 2. How about Elizabeth? How about Jenny? What's 2 times 2 times 2? So 2 possible outcomes, 2 possible outcomes, 2 possible outcomes. There's 8 total outcomes that we need to list. Okay, so I'm just going to quietly list mine up here. You do yours on yours. I'm just listing out all the outcomes that could happen. I'm not worried about who's paying for coffee. I'm just going to list out what they could get when they toss their coins. And for some reason last semester, I couldn't say toss their coins. Every time I tried, I kept saying toss their cookies. Okay, so do you have all your 8 of them there? So yours might be organized differently than mine, but we should have the same 8 out. Okay? So let's just go through the rules here. I'm just going to focus on the second bullet. If all students throw the same outcome, then each student pays for their own coffee. So this one and this one, they each pay for their own, right? They either all toss heads or all toss tails. So that is this one. They each buy their own. So that's 2 out of 8, which is 1 and 4. There is nothing telling you that you have to do part A before part B. You want to attack these questions in whatever order makes sense to your brain. Okay? So in all the other cases, somebody has tossed differently than the other 2. That means that person is buying. So I'm going to use a green highlighter now to highlight who is buying in each one of these. So in this scenario, Jenny is buying because the other 2 tossed heads. In this scenario, she's buying because the other two tossed heads. Here, Rebecca's buying because the other two tossed heads. This one, Rebecca's also buying because the other two tossed tails. Tossed heads, tossed tails. Okay? Does that make sense? So, what are the odds that Rebecca buys all three? So Rebecca has to buy here, and Rebecca has to buy here. So 2 out of 8 again. Okay, now last one's a little tricky. Jenny gets a free coffee, meaning she's not buying a coffee. So Jenny buys here, and Jenny buys here, right? But here she gets a free coffee, here she gets a free coffee, here she gets a free coffee, here she gets a free coffee. Does she get a free coffee for the yellows? No, because here they each bought their own. So how many times does Jenny get a free coffee? 4 out of 8. So she's got a 50-50 shot. Actually, each one of them, it's a pretty decent game. Each one of them has a 50-50 shot of getting a free coffee, which you wouldn't think of because there's 3 people at play. But when you list it all out, it actually works out to be that way. This is kind of like perms and cons where you don't expect the answer to be what it is. It's like, ooh, that's a really big number, but it is the answer. Okay? So with these questions, you just want to dial it down. You just want to kind of take your time with them, right? Take your time. I really need you guys to understand that in class, so over the next 2 weeks, we're going to do close to 80 questions over 2 weeks. That's going to boil down to like 5 on the diploma. So everything we do in class is overkill, okay? Everything we do, because I don't know what 5 they're going to pick. Okay, so if you want to just practice some of the basic ones, go back to 3 and 5. Definitely try 7 to 11. Make sure you can get the answers that are on the answer sheet, okay? Because those are more the problem solving.